Hello, my name is Benjamin Hertzsch. I'm a first-year PhD student at the University of Edinburgh, advised by Joop Veldpove, and I would like to present our recent work on the complex evaluation of angular power spectra. I would like to motivate the problem with this illustration of the recent DESI data. As cosmological surveys look out in the sky to measure clustering information, they observe three-dimensional fields. In principle, the radial and angular directions are equally important as both contain physical information. However, in practice, a survey kernel looks out to some redshift z and is sensitive to some redshift interval delta z around this redshift. The clustering is then observed over a large angular patch within this redshift bin. The key observable here becomes not the three-dimensional clustering information, but rather the projection of the clustering information from this redshift bin on the angular scales of the celestial sphere. This is particularly relevant when combining several kernels with different redshift sensitivities in order to calculate auto and cross-correlation angular power spectra. The angular power spectrum is defined by this three-dimensional integral. Here, P is the three-dimensional power spectrum between the two tracer fields, and the deltas are the line-of-sight source functions, which take the form of a kernel multiplied by the spherical Bessel function. Note that more general forms of the line-of-sight source functions are relevant, for example, for shear kernels and for redshift-space distortions. However, we ignore them here and only come back to them on the last slide. The pipeline for calculating angular power spectra is illustrated on the right-hand side, where if we observe the fiducial power spectrum, say, through some survey kernel, which here would be, for example, a cluster-type survey kernel, then we obtain this angular power spectrum, which projects the clustering information on the angular scales. Naively, the angular power spectrum is a three-dimensional integral over an oscillatory integrand and is thus very difficult to evaluate. However, an important simplification that is usually applied is that of perfect correlation. By ignoring unequal time correlators, the power spectrum between the two tracer fields reduces to the geometric mean of the power spectra of the two tracer fields, illustrated here. This separates the chi integrals and turns the CL into an effectively two-dimensional integral. Nonetheless, CL is still difficult to evaluate using brute force methods due to its highly oscillatory nature. We will, throughout this talk, study the oscillatory integral FLK, which is the spatial integration of the source function. One way to model the FLK integral is given by the Limber approximation, which assumes that the FLK curve is dominated by the first peak of the Bessel function. In this case, the expression for FLK reduces to the evaluation of the kernel at a particular co-moving distance, and CL can be efficiently evaluated as a one-dimensional integral over Fourier modes. The Limber approximation is a good approximation for large multipoles and wide kernels, as well as in the case of cross-correlations for overlapping kernels. However, the Limber approximation famously fails for low multipoles and for kernels which are localized in redshift, and in the case of cross-correlations for kernels which do not have significant overlap in co-moving distances. This necessitates the study of robust non-Limber methods for upcoming analyses. In fact, a recent code challenge compared and benchmarked some of these proposals. We will here propose another method that is motivated by the study of oscillatory integrals. Oscillatory integrals are ubiquitous in physics, but they are numerically challenging to evaluate. Consider, for example, the Fresnel integrals, that is the integral of cos x squared and sin x squared, which is typically evaluated from minus infinity to infinity in wave optics problems. If we consider the integral from minus t to t and let t go to infinity, we observe that because of the highly oscillatory nature of the integrand, the integrals only slowly converge to the true value. In fact, this convergence is not absolute, but rather conditional. And if we plot the integral st against dt, we see that the result spirals on this Cornu spiral around the true value. The true value is only reached as t goes to infinity, which will obviously lead to numerical issues when using numeric integrators with, say, a large t cutoff. If one wants to integrate the Fresnel integrals from minus infinity to infinity, one can make progress by complexifying the problem and introducing an auxiliary function, which in this case would be the exponential, of which the cosine and the sine are the real and imaginary parts, respectively. Considering the integrand e to the iz squared and integrating it from minus infinity to infinity, one finds that the Fresnel integrals are simply given by the real and imaginary part of this integral. But now note the complex structure of the integrand shown on the right-hand side. In particular, it is noticeable that the bisectors of the complex plane quadrants are contours of constant phase of the integrand. This means that if we rotate our original integration contour to the contour passing along these bisectors, we get a non-oscillatory integrand and can thus efficiently evaluate a non-oscillatory and absolutely convergent integral along this new contour. This application is in fact an example for the more general theory of Picard-Lefshetz theory, which provides a prescription for the optimal complex integration contour for a general analytic function. This is particularly relevant for oscillatory functions defined on the real line. By analytically continuing these functions into the complex plane, one can find the function's saddle point, and from the saddle points construct the manifolds of steepest ascent and descent, along which the integrand is non-oscillatory. The steepest descent contours are also known as the Lefshetz thimbles, and Cauchy's theorem now allows one to deform the integration contour to pass through the sum through a set of these Lefshetz thimbles with numerical coefficients and sigma, which take either the value -1, 0, or 1. A priori, it is not clear along which thimbles one should flow to recover the optimal integration. However, Picard-Lefshetz theory gives an unambiguous description for this by realizing that the factors ns are simply given by the intersection numbers of the ascent manifolds with the original integration domain, in this case the real line. This means that Picard-Lefshetz theory, without any approximation, provides an exact and optimal prescription for evaluating an oscillatory function in the complex plane. These ideas were first introduced in physics by Witten in 2013 and have in the past decade been applied in quantum cosmology, wave optics, and quantum mechanics. We will, in the following, exploit these notions to efficiently calculate angular power spectra in the complex plane. To this end, we follow the proposal of Feldbrugge and consider a Gaussian selection kernel. Using this Gaussian selection kernel and analytically continuing the integrand of the FLK function into the complex plane, we find that this is the result for our integrand. As you can see, the function is highly oscillatory along the real line, but we cannot yet identify any relevant structure in the complex plane. This changes if we consider again the idea of the auxiliary functions and consider the Bessel function as the real part of an auxiliary complex function. This is done by using the spherical Hankel function. If we now consider this Hankel integrand, we can see that a beautiful saddle point indeed appears in the complex plane, and that we may exploit the saddle point to efficiently evaluate the FLK function for the Gaussian selection kernel. We will thus now in the following investigate this integral of the Gaussian selection kernel times the spherical Hankel function from 0 to infinity, and by taking the real part of this, we recover the original definition of the FLK function for the Gaussian selection kernel. We can in fact calculate the saddle point by considering the large Z asymptotic expansion of the Hankel function. This is given up here. Using this asymptotic expansion and the Gaussian selection kernel, we can readily see that the saddle point is to first order enlarged argument given by this expression. Note the factor of I so that it is indeed a complex saddle point. Cauchy's theorem now allows us to shift the integration contour from the real line to the line in real direction passing through this saddle point, which you can visually see does coincide approximately with the contours of constant phase. If we now plot the Hankel integrand both along the real line in green and along the complex contour in blue, then we can see that the real line contour is highly oscillatory and much larger in amplitude, with most oscillations cancelling upon integration, whereas along the complex contour the integrand is nicely bell-shaped. but this allows us to express this bell-shaped integrand itself as an approximately Gaussian function and perform a saddle point approximation. This is done in the red boxed equation, which is the standard expression for a saddle point approximation, where curly n, alpha, and beta are the integrand, and the integrand's logarithms, first and second derivative, all evaluated at the saddle point. Note that we are exactly at the saddle point alpha vanishes, and so the exponential turns into 1. We included the exponential here to account for a correction in case that we are approximately at the saddle point, but not exactly there. In any case, using this saddle point approximation, we can express FLK by an analytic formula, and CL reduces to a one-dimensional integration of this analytic formula over a range of k values. Note though that we have to distinguish two cases for the large k and the low k regime. When k is large and the Gaussian selection kernel overlaps with the oscillatory tail of the spherical Bessel function, then the method I just presented is applicable, and we can use the Hankel integrand to perform a saddle point approximation. However, if k is low and the selection kernel does not overlap with the oscillatory part of the spherical Bessel function, but rather with the part before its first peak, then we can similarly evaluate the integral using a saddle point approximation, but this time using the Bessel integrand and performing a saddle point approximation on the real line at x is mu, which is the approximate maximum of the integrand. I will not further comment on the Bessel function saddle point approximation, as our numerical studies show that this is a very good approximation. We will focus on the more challenging Hankel function saddle point approximation. Let us study this more over the relevant parameter space. Firstly, notice that so far I have been speaking about Gaussian selection kernels, which may have appeared as a drastic simplification that is not particularly suitable to the physical problem. However, it turns out that radial basis interpolation theory allows us to express any kernel as a weighted sum of Gaussian basis functions. The operation boils down to a single matrix inversion and can thus be done very efficiently. And the advantage of doing so is that using the weighted sum of Gaussian basis functions, we get an analytic expression for our integrands. So we can use the saddle point machinery I just presented. And secondly, sigma turns into a free parameter and can efficiently be used for numerical tuning our method. In short, if we use narrower Gaussian interpolation kernels, then our method is expected to be more accurate. Using the Gaussian integrand, we study our method over the full parameter space, in particular for the L and K, which are relevant as the multipoles and the Fourier modes for which the power spectra have significant support. Mu and sigma are given by the relevant ranges of cosmological survey extent characteristics. Note though, since we are interested in the interpolation of a general survey kernel through small sigma radial basis functions, so we consider also a smaller range of sigma. We quite commonly notice that if we are at a general point in the parameter space, our first order Hankel function saddle point approximation may not be accurate. An example is shown on the right hand side where the exact saddle point is far away from the first order approximation, shown in gray, and the integrand is both oscillatory along the real line and along the first order complex contour, and we really need the exact contour passing through the exact saddle point to do a saddle point approximation. We therefore study our saddle point approximation method over the relevant parameter space and show here a suitable numerical error as a function of L and mu for different slices of sigma. Notice that as sigma goes to 0, the saddle point approximation becomes arbitrarily accurate, but as sigma goes large, only the exact saddle point method can be used. However, using a suitably chosen sigma, the result is that we can indeed use the saddle point approximation for any point mu and L in the relevant parameter space. And notice the complementarity of our method with the Limber approximation. In the large L regime, where the Limber approximation starts to work well, our method is performing less well, and the same applies to mu in the very low mu regime. We have now motivated the need for the exact saddle point of the Hankel integrand. We could now proceed and numerically tabulate this saddle point for the whole four-dimensional parameter space. However, it is more suitable to use an analytic expression which approximately gives the saddle point as a function of all problem parameters. We use perturbation theory to find such an expression, and we omit the details here, but the resulting function for the perturbatively calculated saddle point allows us to accurately trace the saddle point over the relevant parameter space, and so to do an accurate saddle point approximation. This is shown exemplarily on the right-hand side, where we compare a particular FLA function with the exact integral, the limbo approximation, and the first-order exact and perturbative saddle point approximation. Notice that the exact and perturbative calculation results agree to outstanding accuracy with the exact integral, and that in particular the perturbative saddle point approximation result is near indistinguishable from the exact saddle point result. We summarize our method in this box. So in the low k regime, we use the saddle point approximation of the Bessel integrand, and in the large k regime, we use the Hankel function saddle point approximation as we have just discussed. With this prescription, FLK can be analytically evaluated over an array of k values without any integration. Finally, the angular power spectrum can then be efficiently evaluated as a standard integral over the FLK functions weighted by the power spectrum. An example of this is shown on the right-hand side, where for the same kernel that we have used throughout this talk, we demonstrate the exact angular power spectrum and the angular power spectrum calculated using the saddle point approximation. And as you can see, our error is well below 1% level. Note also that so far we have been speaking about the source functions which are applicable to clustering kernels, but our method indeed extends to more general integrands, in particular shear kernels, and should also in the future extend to redshift-space distortion spectra. An interesting open question of research is whether or not we can actually use the same machinery to avoid an integration altogether by considering a complexification of the Fourier integral and potentially summing over suitable saddle points in both chi and k. To summarize this talk, I would like to have shown that Picard-Lefshetz theory allows one to turn oscillatory integrals into absolutely convergent complex integrals, and that auxiliary complex functions may introduce suitable saddle points into the problem, and in particular here that the spherical Hankel function allows us to evaluate angular power spectra as a one-dimensional integration of Hankel function saddle point approximations. Thank you very much for your attention.